The aim of this presentation is to tell you a little bit about the ion implantation facilities at the Surrey Ion Beam. So what's so great about an ion beam? Well, start with the charge, that's the main thing. With the charge, it enables us to separate individual masses with the magnetic field, gives us the possibility for isotopic purity, let alone just elemental, but we can get down to the specific isotope if we want to. Also, in an electrostatic field, we can manipulate the beam, we can scan it across the surface, and that gives us capability to get to a very uniform delivery, and in most cases better than 1% uniformity across 6-inch to 8-inch wafer. With the charge also, we can literally count the ions as they arrive at the surface. As they come penetrate the surface, we can collect the charge, we can count the ions as they come in. So it gives us a pretty good control on the absolute amount of material arriving at the surface. And the difference in voltage between the ion source and the target controls the velocity of the particle as it comes through, and hence how deep into the material it goes. So we have very good control on the purity of the material, the uniformity that it's delivered at, the absolute value that goes in there, and the depth of penetration into the material that we want, the material that we're using. All these features are really useful for industries like the microelectronics industry, where they want at that level of control to make circuits as small as they are. And it's that kind of control that's enabled microelectronics revolution to a larger or less extent. So here at the Surrey Ion Beam Centre, we have two ion implanters. One which is a high energy implanter, which is 400 kV up to 2 MeV, and one high current implanter, which typically goes from 20 kV up to 200 kV. We have a deceleration lens that we can place in front of the target, which will allow us to drop the energy down to about 2 kV. So we can have an implantation range from about 2 kV up to 4 MeV if we use doubly charged particles. We have fairly substantial beam currents, although too high a beam current might cause undesired temperature or heating of the sample. So we do have to sometimes limit that, particularly for the high energy cases. Sample sizes can be up to 40 centimeters by 40 centimeters, although typically we run a little bit smaller than that. We do have a hot stage which goes up to 700 centigrade, and we can go down in temperature to about 10 Kelvin. Sample chambers are in the class 100 clean room for semiconductor work. We do run pretty much any element in the periodic table. The ones marked on the chart there in red are usually radioactive species, so we try not to run those. The ones in green we have run at some point or another for somebody. There are currently, I think, 2 elements in the periodic table we haven't run for anybody yet, so there's a challenge for you. As we said in the last presentation, we also have an implant line on our 2 million volt tandem accelerator, which does allow us to go up to 10 MeV for some heavy ion irradiation as well. The beam currents are significantly lower on this machine. It is useful for some applications as well. We also have 2 fairly newly commissioned single ion implanters. We have Simple 1 and Simple 2. Simple 1 is a liquid metal ion source, a focused ion beam, and Simple 2 is based around the dual plasmatron source. Simple 1 gives us availability of most of the ions of interest for single ion implantation for quantum technology work. Simple 2 is a dual plasmatron source, which gives us access to things we can't get from a liquid metal ion source like nitrogen and potentially oxygen. So it does allow us to do other ions of interest. The idea is that the simple machines themselves give us a spatial resolution of about 20 nanometers, so we can ideally place 2 atoms with a 20 kV energy within 20 nanometers of each other. The Simple 2, based on the dual plasmatron source, the spatial resolution is a little bit less good, about 40 nanometers rather than 20 nanometers. Well, here we are in the implant lab, just having a look around. So there's the Danphysique machine, that's the 200 kV implanter, just walking past between it and the 2MV Van de Graaff accelerator. That's the Van de Graaff there, just walking past it, and now we're coming to the end chamber, one of the end chambers of the Danphysique machine. It's the one that's in the lab rather than in the clean room. It's our line 2. I can take samples up to 40 centimeters by 40 centimeters. This is the control desk of the 2 million volt implanter, the Van de Graaff. This is the end station of the Danphysique, and this is the view of the beamline that goes into the clean room, and there's the clean room inside there where we have the end stations of the 2MV and the principal one from the Danphysique implanter. Go up over the bridge, over the beamline, we look back on the lab and see the 2MV etc. in the distance, and the big magnet, 90-degree magnet, and shaping coils that go into the clean room. So now we're outside the Simple lab. We'll go in and have a look at the 2 single line implanters. This is the dual plasmatron single line implanter. That's the control rack. That's the liquid metal ion gun single line implanter. The liquid metal ion gun has a resolution of 20 nanometers, and the dual plasmatron resolution of 40 nanometers. Dual plasmatron is used mostly for oxygen and nitrogen and inert gas implantation that can't be not available on the liquid metal ion source. And that's just the control desk. So looking back over the lab, Simple 1, Simple 2 and Simple 1. And just to finish up, it's important to note that we also control and run 2 standard focused ion beam system, 2 FIBs, as well as a development system for new sources and source materials for liquid metal ion guns. There is more detail on these in the poster session that you might want to look at. In fact, there's quite a lot of things in the poster session that might be of interest to you. We also house semiconductor annealing equipment, as well as standard electrical characterization and mapping facilities, all housed within a Class 100 clean room. Just worth saying, we also operate under an ISO 9001 certification.